Okay, hello, my name is John Lakos. I work at Bloomberg. This talk is under construction. I want to warn you that I've been working on it, literally trying to get the title slide on right now. And we're going to look at the first half of what will eventually be a complete talk on modules. The other thing is that when I originally posted the abstract, it was done very quickly a long time ago when I had the hope that the modules TS would be sufficient to actually give this talk, and it isn't. So I am not going to give examples in terms of the current TS because that would waste everyone's time. What I am going to do is I'm going to talk about what the requirements are for large-scale development in large corporations as I see it, and I seem to be getting some sort of traction with this as there are a number of people who are working with me to try to produce something that is good for everybody. Let's just put it that way. I also was not able, with all of my technology, to figure out how to put the title slide on the deck that I have. So I have two decks, the title slide and everything else. So I apologize for that.
Is this somehow reflective of budget as well?
Yes, this is really reflective of the way I do things. I get them done, maybe not ideally, but this is something that had to be done by right now, and this is how I was able to do it. So, interestingly enough, this talk is not new. In fact, the same sequence of symbols is going to be observed, but we're going to interpret them differently. So this is kind of a violation of the one definition rule in that sense. There is one set of slides, but I'll talk about modules in the context of how we do development. Now, interestingly enough, what I've been calling components for a long time are remarkably close to what modules should be. It's just that components have to be developed by hand, and modules would do that for you, and then some. So that's the idea. So my hope is as I go through what I'm going to explain, which is component-based development, I'm going to say, and if we had modules, and then you'll sort of get an idea of what it is that we're trying to have with modules. And if modules satisfy all the additional requirements we'll talk about in part 2, because there are 4 parts and we're going to do only parts 1 and 2, then we'll be in a good space. The second half of the talk is talking about how we would use modules as an aggregate that's above the size of a component, and I haven't done that yet. I know what I want to say, but I haven't done that yet, and there isn't time anyway, so it's all good. So here's the copyright notice. Here's the abstract. The bottom line is that we need to focus on the architectural benefits as opposed to trying to improve performance. The performance will come, and we have to be mindful that we need that kind of performance, but that is an optimization that happens only once we get the design correct and useful. If we try to go the other way, we will have a missed opportunity that we cannot afford. That's my opinion. So, large-scale C++ software design is multidimensional. It involves logical and physical aspects, something I've talked about for a long time. We have to express the functionality in physical components. Have to express it very clearly in English, but we have to be mindful of the physical dependencies that result from the implementation. And finally, the C++ language itself lacks a mechanism to characterize and render software at a sufficiently high level of logical and physical abstraction, and in particular physical modularity, and that's something that modules can bring to the table. So hopefully as we go through this talk, you'll understand what modules do offer, and also what they don't offer. And it's interesting, people think modules are the solution to all problems, and they are not. They are the solution to some problems. So we'll find out what those are. So the purpose of the talk is to review basic component design principles, component properties and logical diagrams, implied dependency and level numbers, the 2 most important physical design rules, which by the way modules would cure out of the box, guidelines for colocating classes in a component, also known as a module, logical encapsulation and physical insulation, when to include a header file in a header, and that will become very relevant when we talk about imports and modules, and our 3-level physical packaging hierarchy, which we're not going to talk about because that's in the latter half of this talk, which we're not going to give. The second thing we're going to talk about is introducing this thing called a module into the language and describe, in terms of the essential engineering requirements, what it must fulfill in order for it to be adopted widely in industry. So that is what this talk is about. But most of it is talking about what we need as architects to build large-scale software. And then we'll see how modules solve that problem or don't the way they are now. Okay, so this is the outline of the full talk, which we don't have time for, but the first two we do have time for, so we're going to do that. So review of elementary physical design. This is my idea of a component. It has a logical aspect to it, and it has a physical aspect to it. And most people are taught logical design in school, and physical design is something that comes only when we get to the reality of large-scale development. So here we have this abstraction of logical content, and then we have this hierarchy of physical entities. And they consist of components. And in C++ and in my world, a component consists of an implementation file, a header file, and an isolated test driver to exercise this thing. The current thought on modules is it looks a whole lot like this. It has an interface and some number of implementation files. Now, for simplicity, let's just say one for now. We can talk about whether we need many. And in fact, a component exists if it has one interface and 0 or more technically, but 1 or more implementation files. But we haven't found a need for that because one gets the job done, and again, it's a whole methodology that fits together and has worked for a quarter century, so we let it be. This is the fundamental unit of design and has been, I said a quarter century, it's even more than that, for a very long time. And modules are this and this is modules. They're really the same thing. It's just that modules offer more because they can, because they're part of the language and they're not something that we do outside the language. All right, so a component is not just a .h.cpp pair, nor is a module. So let's see what the properties are of these. Now, some of you have seen this before because I've been giving this talk forever. Okay, so the first property of a component is that it includes its header file as the first substantive line of code. Now, it's an interesting coincidence that modules implicitly import their interface. How they do it is magic, and that has to be worked out. But interestingly enough, they have this property. By design, it's kind of like you don't have a choice. Good job. Why is it that we want to include the header file as the first substantive line of code? Does anybody know?
Make sure it's self-sufficient.
Make sure it's
Self-sufficient.
Self-sufficient with respect to compilation. In other words, you don't need to include anything else, it will compile. That eliminates an age-old problem called include order dependencies. That's a good thing. Modules want to avoid that. So this is one way to avoid that. You'll see the duality, it's scary. We don't want to have an empty .cpp file because we want to include the header file in the CPP file to know that it compiles locally so that we don't have to discover that later. The second one is, this is what I've been working on extra slides for, because when I gave this at Bloomberg, people said it would be nice if you had some slides to explain what this slide means because it's kind of dense. So all logical constructs having external linkage defined in a .cpp file are declared in the corresponding .h file. What does that mean? Okay, well, first of all, we have to understand some things like declaration and definition. And we use the terms all the time, but are we crisp on what they mean? So what's the difference between a declaration and a definition? What is a declaration? Would somebody like to volunteer what a declaration is? Sir?
Promise of a definition.
Promise of a definition. Ooh. No, not really. Another try.
Introduction of a name.
Into what?
Into a namespace.
Yes. Introduction of a name into a scope or a namespace. Excellent. That's what a declaration is. All right. What's a definition?
Everything you need to know about it.
All right, that works. Everything you need to know about it. So a declaration isn't necessarily everything you need to know about it, but a definition is. All right. That'll work. Let's go with that. So I have int a. Is that a declaration, a definition, or both? Declaration and both. Which is it? Both or a declaration? It depends. This isn't file scope. And it's C++. Is it a definition, a declaration, or both? It's a definition, but it's not a declaration.
It's also declaration.
Somebody who actually knows the answer, will you just tell me? Both. All right. Jeez. All right. I know that it's, hard question, but we got to answer these questions. Let's try again. What about extern int a? Is it a declaration, a definition, or both? I feel that we're learning. Extern int a equals 0. Yes, both. Void f, open, close, semicolon. Is this slide useful? Because I didn't have this when I talked at Bloomberg, and I was saying these off the top of my head. Yay! Good job. All right. Now we need to know about linkage. What's linkage? What?
Visibility of the name.
The visibility of the name. In what versus what, for example?
Translation units.
Across translation units, and if it's visible across translation units, then it has what kind of linkage? External. And if it doesn't? Or no linkage, right? Okay. So it could have no linkage, or it could have linkage that's within a translation unit. Those are kind of the same for our purposes. Or it has external linkage, which means it crosses translation unit boundaries. Sometimes people confuse translation units with modules. Okay. Think about that one. So int a, does it have internal or external linkage of file scope? We could translate file scope for namespace scope. What is it? Internal or external? Excellent. By the way, I did these slides within the hour. So if I made a mistake, I do apologize. I actually do know the answer, but I might have mistyped it. I didn't have time to check it, and I even had one more slide I wanted to do, so I apologize. It'll get better. Static int a, internal or external? How about this crazy thing? A function definition. How about this one? How about this one? Ooh. Whoever said internal, have you been programming for more than 20 years? Because those are the people that might say internal, I suspect. Because at one time it was internal. It's external. What do I mean by linkage? The name is the same, theoretically. The name means the same thing in separate translation units, right? Okay, so I can have an inline function in multiple translation units, but it has to do the same thing. If it doesn't do the same thing, what rule does it violate? ODR. Okay. What about this? Internal or external linkage? Okay. Class foo. Excellent. How about this one? Good. This one? Good. And this one? Okay. Now, this is a declaration. This is a definition. What really has the external linkage is the definition. Okay. And if the definition can be referenced from another translation unit, then it has external linkage. Does that make sense? Two declarations refer to the same thing and they're in distinct translation units. Then the thing they refer to has external linkage. So I was playing fast and loose here, but you get the idea, right? Okay. Let's keep going. Namespace class foo. Internal or external linkage? How about this? 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 It's not really something that can have a linkage. However, if you have two namespaces in separate translation units, they are the same namespace. So this is kind of a funny one. Don't worry about it. It's external-ish. Class foo? Static int. What is that? That's the definition of something that has external linkage. It's the one that does have the external linkage, and the other one's a declaration of it. How about this one? Doesn't compile for two reasons. It doesn't compile because we already defined it up here. And if we took that away, it wouldn't compile anyway because it's not in the same namespace as the other one. So either way you look at it, this won't compile. But this one does compile.
But it's also not in the same namespace.
Interestingly, I tried it. I would have said that it shouldn't work, but it does work. And I guess what's happening is that there's an implicit including directive for the unnamed namespace into the current translation unit. I'm guessing. I don't love namespaces, except for specific purposes. So when we get into this kind of thing, I have to go try it.
That doesn't actually have a namespace. It's just saying that they are static, right? It's kind of
In the current world, the unnamed namespace and static have the same semantics. That was we undeprecated static, and so they mean the same thing. They were forced to mean the same thing, but for a while they meant different things, and it was problematic, and you couldn't use a template couldn't refer to a static method of a class and all that, and that was all fixed. So anyway, I just put this out here just again. It's we like to learn a little something that's useful in our day-to-day work, so this might be useful. Right? It's just that the last definition is, broken. Okay. Does this make sense? Now, if I had time, I would have given you an example of what bindage is, but I ran out of time, so I'm going to just use my words. All constructs have, what I should do? I should explain this rule now that I've explained everything else. Let me go back and explain. This is something I should probably come back to. So I'm going to add a slide that goes back to this rule. All logical constructs having external linkage defined in a .cpp file are declared in the corresponding .h file. What that means is, this is the point of the rule. If you have something that can leak out into the object level ABI, you want a programmer to be able to see that in the header. You want that to be obvious. You don't want that to be a little dirty secret that no one knows about. So what we're saying is, if you're going to leak, if you're going to go outside your translation unit, don't do it quietly. Say so. Say so somebody can see it. That's what it means. Okay? Note to self. Put the slide back and talk about it. This one doesn't have any supporting work, so I'm going to tell you what it means. All constructs having external or dual bindage declared in a .h file, if defined at all. Remember somebody said a declaration promises a definition? Not necessarily. Are defined within the component. So what that means is, if you're going to declare something where the linker can get involved. See, bindage has to do with what tool binds the use of a name to its definition. The use to its definition. I know this is true because I made up the word bindage. That's what it means. I couldn't use linkage because it was taken. And linkage means something useful. And it's independent of tools. But bindage is not independent of tools. Bindage is very important because tools are really important when it comes to these things. And in C++, we have three kinds of bindage. We have internal bindage, which is handled by the compiler, always. We have external bindage, which is handled by the linker, always. And then we have dual bindage, which is handled by either the compiler or the linker, at the pleasure of the compiler. We'll just mention that. The compiler gets to decide. And for example, classes, class definitions, have internal bindage because if you think about it, the class definition itself is a bunch of declarations and not definitions. And so the compiler is interested, but the linker could care less. Okay? And even things like type defs, only the compiler cares about type defs. The linker could care less. I remember getting into a long argument with somebody about this. It was very interesting. And this person swore up and down that definitely saw symbols in the linker reflecting a type def. Okay. And then there are things like functions where you need the linker to link the use of the function based on its declaration with the implementation. And we all know that. That's what linkers do. And they do that for global variables, which we never use. And they do that for static class data members, which we use extremely sparingly, I hope. Okay. But what two constructs in C++ have dual bindage? Anybody? Inline functions. What other one? Templates. Inline functions and templates have dual bindage because, and I'm just going to mention an aside, we used to have template repositories, which is one of the things that modules is proposing. We're going to be very, very mindful that that didn't work. And so instead, the A.out format was modified so that we could put a symbol in the .o file that if you used it, didn't bring in the rest of the .o file. And so both inline functions and templates, when you instantiate them and you need them for later, they're put into one of these segments or sectors. And so unlike other things, when you get one of those, it doesn't drag in the rest of the .o, because if you did, nothing would compile. The world would be a terrible place. And each one of these independent things that gets put into every .o every time it's instantiated is precisely the same. Hence, it doesn't violate the one definition rule. So that's how we solve the problem. That means we duplicate it by value in every .o where it's needed, rather than have a central place to refer to it. Does that sound like a good idea? Because experience shows it is a good idea, much better than having a repository, which is what's being proposed. Now, some people haven't lived as long as I have, lived a long time, and I have been through it, and I know how bad that was. Template repositories in the 90s, not good, okay? So we know better, and we know from other languages like Ada that there are good ways to do things that work, and then there are ways that don't work. Just saying. So, back to bindage. What we're saying here is that if a linker needs to get involved, if it might get involved at all, then we do not want a local declaration. We want to be forced to include the header file. We want that. And therefore, what this rule says is you're not allowed to have a local declaration of anything unless only the compiler is going to bind it. Why? Because that means the compiler will eventually, in this translation unit, lay its eyeballs on this thing. And at that point, it can figure out, oh, you messed up. Whereas if the linker is going to do the binding, it's entirely possible you lied to the compiler and said, oh, yeah, it looks like this, but it doesn't look like that. It actually looks like something else. You got it wrong, and it becomes a link time error if you're lucky, or worse, it's ill-formed. The program is ill-formed. We don't want that. So this, very simply, you can say class foo, but don't you dare say void f open close semicolon when f is defined in some other component. Just don't do that. Oh, by the way, the current module proposal allows you to do that. Who would have thought? So that's a rule. That's like not even a rule. It's before a rule. It's like you can't even have a component if it allows that. And yet the module proposal allows that. Needless to say, I'm verklempt. Is that how you say it? Verklempt. Okay. And fourth, there's a really good reason for this. If you're going to use something substantively, do not forward declare it pound included. Always pound include what you're going to use. And the reason for that is actually awesome. It's not what you might think. Yes, it turns link time errors into compile time errors, but what it does even better is it allows you to take the envelope of include dependencies. You could reword that to import dependencies if you're allergic to include files. But get over that. And then all will be good, because now, without having to parse the code, you know that you have an envelope that says what depends on what, at most. Now, it might be a little bit too much. The actual dependencies might not be as bad as the pound includes reflect. But if you follow these rules, which modules would enforce if they were done properly, it wouldn't be a question, it would be a fact. And that would be an awesome thing for everybody. And this has been being done since 1990 by somebody. That would be. So I know this works. And it worked before Clang, because there was no Clang in 1990 as far as I know. And yet I could do very large analyses just by looking at the pound includes. A little Perl script and you're good. All right, so now we can talk a little bit about notation. I bet you a lot of you have seen this. I still need to run through it. So, and we would probably never do a polygon inheriting from a shape, because a polygon is a value semantic type and a shape is an abstract interface, and as we all know, that's oil and water. But for your intuition, we're going to say that a shape has an origin which you can get and set. And a polygon is a kind of shape where you can add vertices, do good things like that. Okay? So since you can get and set the origin, and the origin is represented as a point, we'll say that there's a relationship between shape and point, that polygon is a kind of shape, that polygon is implemented in terms of a point list, and that point list and point list link, which happens to be a private class in that component module, excuse me, this module, component, over here is going to have, what was that? What is this? That was good for it. So anyway, it turns out that if you just replace component with module, all the things that we want to do with components just happen naturally and nicely. But we're doing this by convention, and there's a reason for that in our larger picture. Having irregular nesting is harder to understand than having uniform nesting, and so instead of having a nested point list link class, we have a private point list link class that is at the same level as the public point list, and the point list depends conceptually on the point list link. It doesn't hold it inside, because that's the job of the module, to hold it inside, not the class itself. Anyway, and again, this is something that we've been doing for a long time, because we didn't have modules, and this really works very nicely. And if we had modules, we would continue to do precisely the same thing, not create nested classes, but create private classes within modules. So, that said, ISA. I could go on forever about ISA, but I won't. A polygon is a shape for whatever you think ISA means, as long as it's not Liskov. Don't think that. If you think that, then we have to start over. Because that's just wrong. Let's just put it on the table. Public inheritance, when you have dynamic binding, is not Liskov substitution. Just if anybody thinks that, I'm telling you right now, and I can prove it, I know. It's not true. It's public inheritance. It means that the behavior of the derived class changes depending on what the derived class is. It's not the same behavior. It's different behavior. If it were the same behavior, you wouldn't need inheritance. Okay. Now, and again, I'm talking about inheritance, dynamic binding, virtual functions, and all that, because there's structural inheritance, but I digress. All right, so polygon is a shape. Yes, there are virtual functions here. Absolutely. And a polygon uses point in its interface because it has a function, and the function is add vertex. And if any function that names point in its interface, in its signature, or its return type, uses point in its interface, and Polygon has methods that use point in its interface, therefore Polygon the class uses point in its interface. Same is true for point list and point list link. They use point in the interface. Then we have uses in the implementation. Suppose something uses something, but not programmatically in its interface. So you wouldn't know if I just went inside and took it out and put something else in. You wouldn't know. You might have to recompile. But if we had modules, you'd still have to recompile. If anybody thinks that modules will stop us from having to recompile, think again. Not true. However, modules will help us not to have to rework our code. That's a big deal. So modules do not promise what's called insulation. We'll talk about that later. Modules give us a way not to depend on private types that happen to be public because they were exposed because they're used in the implementation of a class. Does that make sense? So we understand the pimple idiom. If we have modules, the pimple idiom lives. Yes? Note that big important thing. People think that modules will somehow create compile time decoupling, and they will not. Okay. All right. So Polygon has a point list as a data member. That's an imp detail of Polygon. If I were to change that, and somebody happened to have their hands on point list because point list was included in Polygon's header file, they could get hold of point list and start using it, and then if I wanted to change it, I'd still have to support it forever. But if I had modules, that wouldn't be the case. I could use point list as an imp detail of Polygon, but no one could get their hands on it to use it in the future, so that I would be bound to support it forever. Score 1 for modules. I can't do that with components. Does that make sense? Okay. Now, point list also uses point list link in the implementation. There's nothing in point list that talks about point list link, and that's a good thing because point list is a public class of this module, but point list link is not. So we wouldn't want point list link to be in the interface of something that's public when it isn't. That would be weird. And there's a better word for weird, but it would require too long to explain, so we'll just leave it at weird. Don't do that. It's a poor man's encapsulation. Poor person's encapsulation. All right, this is a very strange relationship. This is the only relationship that does not imply a physical dependency. It's called uses in name only. It doesn't require that I pound include point in order to name point in the interface of shape. I don't have to include point at all in order to have a shape component as long as it's a pure abstract interface. That's interesting. So this is unique in all of our notation. This is unique. Does not imply a physical dependency. All right. Depends on. That is a physical dependency. You'll note that all of these logical relationships are across logical entities, those bubbly things. But the physical entities, the rectangular things, have dependencies. So Polygon's component or module depends on shape's component or module. Polygon's thing depends on point's thing, its physical container. Both point list and point list link use point. Therefore, that thing depends on point. And finally, Polygon uses point list, but not in the interface, but in a substantive way. Therefore, Polygon depends on point list. So even though it's not used in the interface, there is a physical dependency. Okay. Level numbers. This is ancient, but I'll just mention it. You can take an acyclic directed graph and assign numbers to it in a meaningful way. If you start with something that doesn't depend on anything else, is not pointed to by anything else, we just arbitrarily say those things are at level 1. Point is at level 1. As I mentioned, shape does not depend on point because this does not introduce a physical dependency. There's no include. So it's also at level 1. Somebody tell me what level the component that implements point list is at. 2. How about Polygon? Okay. Enough said. Everybody, this is good, right? What's good about this is now I have a methodology, a roadmap for testing. And now I can test point, and yes, I can test shape. Yes, I can. Independently of anything else. Then once I've tested point and shape, don't really need shape, I can test things at level 2. And once all the things at level 2 are tested, I am in a good place to start testing things at level 3. And everything at level 2 can be tested independently of everything else at level 2. Think about that. Does anybody do testing, by the way? Is this important? I'm serious. Is this important that you know that you can test things in terms of other things that have already been tested, or is that just nice? It's more than nice. It's how we get things right. Just flat out, if you can't do that, something's broken. And you know it. I'm sorry. All right. Physical design rules. This is a big deal. I don't know why, but for some reason modules solve this problem out of the box, both of them. What are the two things that we will not do that modules will not allow us to do? Except they do, according to the current spec. But we will ignore that because that will not be allowed to stand. Will not. Over my dead body, even if I'm dead, I still won't allow it. What's the first and most important rule of physical design? Period. Yes, of course. There are two. The first one is no cyclic physical dependencies. Modules will not have cycles. They will not have cycles. The other thing is, there will be no such thing as a friendship that allows you to go inside a module and use its private data. That will not happen. No long-distance friendship, and no inter-module friendship. Period. That will happen. This one I think everybody agrees on, and I think somebody was just up a little too late one night and said, wait, we can work around this. No, we're not working around that. For the good of humanity, we're not working around that. Okay, then the next one is the criteria for collocating public classes. Now remember, the linked list, the point list link was a private class. It's not accessible outside the module. So we're not talking about that. But why would you have two public classes in the same module? Also known as a component. Why? So one reason is friendship. If the two need to know about the internals of each other, then they have to reside in the same module. If there's a cyclic dependency, for whatever ridiculous reason, and since I wrote the first book, and the second one is coming out this year on pain of death to me by everybody, there are cases where you need a cyclic dependency. They are so few and far between, it's unbelievable. But there are extremely rare cases that have to do either with recursive templates or with certain kinds of optimizations where you just go, you know, all right, we're going to do that. But they're so rare it's not worth talking about. They are vanishingly rare, and so this really isn't a reason. If this is the reason, it means you didn't think hard enough, most likely. Almost certainly. The third one is called single solution. And before we had variadics, we might need to put a bunch of things in the same module or component because together they solved a problem. For example, a variadic template, if you had to have many implementations with varying numbers of arguments, together they solved a problem that now we can do with one construct. But we couldn't before, but that's just because the language hadn't evolved to the point where we could. So this would be an example of where we would approximate a single construct with many, and we'd say that's okay. What's salient about this particular thing is there are no dependencies together. They're collaborative and they provide together a solution. That's critical. Now imagine you have a different thing. I have, for example, a coordinate, a point, a box collection, and a garage. Someone might say, how am I supposed to use a box collection without a box? That's silly. Of course I'm going to put the box in with the box collection. How many people think that's a plausible argument? Not raising your hands. Why? Why isn't it a plausible argument? There's a real good reason. You can use box by itself. So just because the person who's stuck with using box collection has to use box. The other way around isn't true. And so remember that you may be able to reuse something that's smaller without the thing that's bigger, and don't let the bigger thing tell the smaller thing what to do. Right? That's bullying. Don't do that. Bad idea. So what you want to do instead is separate the coordinate into its own reusable piece and then build a point out of a coordinate. And then hierarchically build a box out of a point. And then hierarchically reuse the box in a box collection, and then hierarchically reuse all of them in a garage. Hierarchical reuse is extremely important to avoid reinventing the wheel over and over again. Does it take more time to get something right the first time? Of course it does. Also, by trying to get it right the first time, you get other things right the first time because you learn something. Otherwise, you just write a bunch of garbage and you continue to write garbage and it's not good. So don't do that. Write things carefully. Now, I'm an infrastructure developer kind of person. I was an application developer kind of person for a brief period in my life. I still wrote it like it was infrastructure code, but the idea is that if you're writing infrastructure code, it's so leverageable. It's so important. It's worth the extra time. And it's one of those things where you're investing and you're going to be paid dividends. And you really are going to be paid dividends. And it takes a while. But once you get there, you never look back and you'll never regret it. So just saying, I know this. It takes time. It's worth it. This is fine. And the fourth one is called Flea on an elephant. And this is an engineering trade-off because things aren't absolute, right? When you get to the edge case and you have something that's tiny and you need it with the thing that's big, sometimes it's okay to package those things together. And the example I tend to give here is that you have a scoped guard and a logger. And the logger needs to be initialized in main and then destroyed at the end of main, let's say. And the scoped guard depends on the logger, and all it does is call those two functions. No big deal. Two inline things. It's nothing. It's just a flea. The logger is an elephant. It has all these dependencies. It does all this file stuff. It's a big deal. Having these two things in the same component does no harm whatsoever, and it allows you to write a usage example that refers to the flea. Otherwise, you'd have to make up a flea and say, suppose we had a flea. Then you have to write a flea, and then it's no. On the other hand, suppose this is a point, and this is a graphical engine. You say, I want to use the point. But unfortunately, to use the point, you have to take the graphical engine with it. That's crazy. That's the other end of the spectrum. We would never do something like that. But the idea here is, if we did this, we would have a horrible design. So this is a bad idea. But there's a tendency to abuse this thing called flea on an elephant and introduce other organisms or farm animals like a goat and a pig or something like that. Don't do that. Keep it something really small and something really big, and if it's anything else, keep it separate components. This is only for the most extreme case. Another example of this, by the way, is operator double equals on a value semantic type. You could write operator double equals without having private access most of the time. And still we put it in the same place for two reasons. One, it's a flea on an elephant. It's part of that abstraction. And two, if you write an operator outside of the component or module in which one of its types is defined, it can get lost. And then if two people do the same thing, and then later somebody incorporates both header files, let's say, you wind up with multiple definitions. You don't want multiple definitions. That's bad. So the way you avoid this is you do it in the same component so there's one place to look, one place to find it, and that's where it belongs. Or you don't make it an operator. You actually make it a function in a named utility. That solves that problem. But again, the reason I mention it is operator double equals on a value semantic type belongs in the same component, and it is an example of a flea on an elephant. Okay. So we just talked about physical packaging and things like that. We need to talk a little bit about the other side of the coin, which is insulation. Does anybody have any questions on the first part of the first thing? How are we doing? Yes?
What about argument-dependent lookup? Should you put functions that are supposed to be found by ADL in the same component as the corresponding type?
Okay, so we have like the world expert on this subject asking me a question about ADL. All right. So my answer to this is, I don't like ADL. ADL is not my friend. In fact, I didn't realize that the way that I code prevents a potential problem in ADL. Somebody had to tell me because I never encountered it. And the thing is that when we create utilities, which are a lot like templated algorithms, but without the templates, when we create utilities, we put a named function in a struct. And it's a static method of a struct. And as barbaric as that sounds, it neutralizes ADL. But we didn't want ADL because we wanted to call the function. We wanted to call this function. We didn't want to look up anything. We didn't want to introduce it. And we didn't ask. We don't want it. Please keep it from us. The only time that we want ADL is when we have a function that acts like an operator. So swap, for example. We would want swap to behave just the same way as we would an operator, and we would want all of those things to play in the ADL space. But since we don't allow free functions at all in my methodology, unless they're like swap, where they're supposed to be operators, but we ran out of operators, this doesn't come up. And it works very nicely. So I don't know if I answered your question, but I'm really saying that it doesn't come up because we don't do it. If we need to do it, we do it, but we need an engineering need to do it. And without the engineering read, static methods of a struct give you a lot of good things that namespaces don't give you. And one of them is they don't give you ADL. So, I tried. By the way, if you want to, it's good. I have been blessed by a higher power. All right. Seriously.
John,
Yes?
I like free functions.
Okay, we have somebody who likes free functions. He happens to work in my company still. Yes?
Why exactly are you against ADL in something like a utility namespace or namespace that can be extended in multiple files where, ADL can happen if you really wanted in that namespace, but it's isolated, so it's like an opt-in ADL.
Okay, so somebody who's far more knowledgeable about this particular issue than I am has asked me a question that I can't answer in real time. So what we're going to do is we're going to go to the gym, we're going to work out, pump some iron, and talk about it, because I have no idea how to answer that. All right. So, encapsulation, an implementation detail of a component type, data, or function that can be altered, added, or removed without forcing clients to rework their code is said to be encapsulated. Historically, encapsulated really means just putting the data with the functions, never mind whether it's private or not. But it has come to mean that, oh, by the way, the data is private, or why would we be doing this silly thing? So encapsulated means that there's no programmatic access to this thing that we have. Can't get at it. But the compiler can see it. It's just that the user can't get at it. Why is that important? Modules will give us that distinction where we can actually have things that are private that can be used by the client but can't be used completely. Can be used by the client through whatever we provide as the interface, but can't be separately instantiated. So encapsulated details are something that modules can enforce much more strongly. An implementation detail of a component, type, data, function that can be altered, added, or removed without forcing clients to recompile is said to be insulated. Components, you use components to do that by tricks like the pimple algorithm and partial insulation techniques, which you could read about either from the 1986 book or this year. There are techniques for doing this. Modules do not help at all. Not at all. Sorry. All right, so let's see what I mean by insulation. Suppose, and by the way, I've done this in reverse. I don't know why, but it seems to work better. So dependencies are going up. This is the only time you'll ever see me do this. Dependencies are going up. They always go down. But the client here, which is at the highest level of dependency, is on the bottom. And the client is referring to a library. And we have an imp detail here. And the library component is using, the library component C is using the imp detail library component D via a pound include in its header file. And so if we change the header file of the imp detail, what happens? What happens is we have to recompile this component, but unfortunately we also have to recompile this one. That means that when we make a change to an imp detail in a library component, the client has to recompile. We say that that D is encapsulated. It's encapsulated, but it's not insulated. Okay? It's an int detail, but the client's going to have to recompile. Now, it's not really the thing itself. What's interesting is that modules can actually make D encapsulated, whereas the way we do things, it's just the use of D. It's not the component itself. Now, we don't want this. We actually, the way we design things hierarchically, when we make something public, we would like it to be available for all to use. Whether we today use it or not is nobody's business. But if we come up with something awesome, we say something like vector. Whether we use vector or not is none of your business. But if you want to use vector, that's fine. So we don't want to encapsulate vector. We want to encapsulate the use of vector. And that's what this is talking about. All right. Now, imp detail E is different. Because E is included in the CPP file as opposed to the .h file of the library component, if we make a change there, yes, we have to recompile the library component, but the client doesn't have to recompile. So we say that E is insulated by C, but really what we mean is E, the use of E is insulated by C. That means if I stop using E, nothing happens to the client at all except relinking. Modules don't help you. I'm telling you, modules do not help you here. Okay. Criteria for having a pound included in a .h file. Why would anybody ever, in their right mind, include a header in a header?
Implementation detail for a template.
Implementation detail for a template. Not sure I understand what you mean by that.
You want to expose a template in your header file, and inside implementation.
Oh, the implementation of the template. Ah, gotcha. Yes. Yes. So I'm going to wrap up template into code that has to be seen by the client, which includes an inline function or a template definition because it, yes, I understand. So good. What's like the most clear reason for doing, like you gotta do this? Inheritance. Okay. The reason inheritance is the right answer, is the most important answer, is because we know that a header file has to be self-sufficient with respect to compilation. There is no way in the world I can have a polygon unless I know the definition of shape. So there are 5. The first one is ISA. In fact, ISA is so strong that if you include polygon.h, you don't need to include shape.h because you know that polygon.h had to include shape.h in order to compile. So it's redundant for you as the client to include shape.h in order to use it. In header file land, now it is an open question as to whether in module land, if I import a polygon, does that mean that a client should be allowed to derive from shape? I'm not answering the question, I'm simply saying it's a question. In every other case, it's not a question. You use it, you import it. That one is open, because that's a separate rule. It stands out. Has a. So if I have a data member like point, or a point list inside Polygon, I absolutely don't want somebody to be able to use point list just because they're using Polygon. Absolutely not. If you want to use point list, then by gosh, you include it yourself, or you import it yourself, or both. Not uses. You would think the next one would be uses, but it's not. So here we have an example of a append vertex, and it takes a point and it returns a point. And what if I were to change that to returning a point, let's say? Is that okay?
Yeah.
It's perfectly okay, because unless I use the function, or unless it's an inline function, the compiler doesn't need to know. So uses is not a reason to pound include. Okay. So inline functions, good reason. If the body of the inline function makes use of it, yes. And by the way, by the same token, a template definition. and enum in C++03. Now C++11 introduces a very interesting, what we'll call attractive nuisance. If you use component-based design and you put an enum class or an enum that has an integer underlying integral type that's different from an int, you specify it, then what that means is you can elide the enumerators and it's still a complete type. And that means that if I have a component or a module that has one export and it exports the whole definition, and you as a client want to consume only the complete type without the enumerators, you're tempted to declare it locally. You're tempted because there's no other way to do it. You have to, unless I provide you a separate way to include just the full complete type without the enumerators. And so I call it an attractive nuisance because there's a real reason to try to declare it locally. And if you declare it locally, it is no different than declaring an int locally, a global variable, or declaring a function foo locally, where the function signature can change and there's nothing to help you. The whole thing about header files that's awesome is that the header file is incorporated with the definition to make sure they're consistent and is then incorporated with the client to make sure the client's use is consistent. Header files are not stupid. They're awesome. So don't throw them out just because you say, oh, they're no good. No, they're good. They're awesome. There may be something awesomer, but they're awesome. And then finally, I say type def to a template specialization. To generalize this, what I really mean is if you've got something that is a template, if you start to add let's say you have a template that's compatible, but you decide to put an optional type or whatever. Now, if you try to forward declare a template, it's brittle. Not so much with class. Class foo is class foo, but templates get to be brittle, so that's a little bit of a problem. And then if you have something like string, which isn't even a template, but it's a particular instantiation to a type def, you can't really just say class string, just doesn't work. So you need to include that there too as well. So there are reasons beyond this, but basically, don't include a header in a header unless you need it so that the thing will compile. If you don't need it for the thing to compile, don't do it. Okay? So that's the idea. Covariant return types is another edge case. Any questions on this? Yes, sir.
It sounds like you are advocating for declaring classes from other components. Do you think that's actually okay?
So say what you said again. Do I saying it's okay to forward declare their classes?
You're saying it's okay to forward declare a class that's defined by another component.
Okay, so the question is it okay to forward declare a class that's defined by another component? For different definitions of okay. So it's in many ways way more maintainable to never do that. Okay, so that's your point, and you know, and I know, that if you declare something as a class and for whatever reason it changes to be a particular instantiation of a template because of growth, it's a pain in the butt to go through and make all of those local changes. That's your point, right?
Yeah.
Okay. This is a increasingly sound argument for not forward declaring even classes. Also, the problems that used to exist in 1998 or 1996 or whatever when I wrote the first book have changed. We didn't need modules in 1996 at all. And now we desperately need them. And the reason we need them is because a lot of the compile time cruft has shifted from the CPP to the header. And so what used to be really cool to just say, oh, I can change the class and nobody needs to worry, isn't as much of a problem because we're dying from compile time changes anyway. So the world has moved. If you have a very stable environment, very stable, you might make the argument that classes provide some, when I mean the interface is stable and you have very well insulated stuff, you might make the argument that classes are a blessing. But Richard's point is very valid, and I can imagine really sound engineers saying it's not worth it anymore and going with never forward declare anything. But at least we agree, never forward declare anything where the linker gets involved. Can we at least 100% agree on that one? And then it's a little bit fuzzier with the, is that fair?
Yeah.
Okay, at least we're qualitatively in the right ballpark. Okay.
And we rephrase it as, if you have control over all the components, then you might consider forward declaring, but if you don't have control over the components you're using, never forward declare it.
Okay, so the point was made, if you have complete control, you might forward declare it, but if you don't have control, never forward declare it. And that's another way of saying, if you don't have a stable system and you're going to need to make non-insulated changes routinely, and in fact, it's not even an insulated change, it's actually an interface change, I take it back. The insulated changes force people to recompile, but what you're saying is people would have to otherwise rework their code because of changes of things that you depend on. So it's not even insulation. If you're making a change where your client is going to have to rework their code, and it's out of your control, then absolutely, I mean, that's just good business sense. We don't do that. Like, we don't make people rework their code almost ever. It's a rare case. It does happen. If you're in a company such as Google where you can just apply a script to a single build system, you have a better case for not doing what I just said. In other words, that would be a stronger, that would be an argument on my side to allow for certain kinds of forward declarations. But if you don't have that, and if you're like Bloomberg that doesn't have that, it's a weaker argument, and at some point it might convince us that, yes, we're never going to ever recommend or suggest. But certainly stability is a factor. Any other questions on section? Yes?
What's your take on with the module shipping forward header declaration, basically, in another file, like a forward.h?
Okay, so for modules, forward declarations, they're really now, we're talking about import statements, and the thing that I am most concerned about is having a module have a statement that pretends to know what some other module's interface looks like and says, trust me, if you could depend on that module, it would say this in its interface. That's allowed right now, and that has to go away. So local declarations in modules that allow you to have cyclic dependencies are absolutely out. And as far as whatever else happens, I could be convinced that even class declarations aren't worth it. You know, I'm willing to give some things up. That's not necessary. Yes? Yes?
I was just wondering there, a lot of what you're arguing against sounds to me one of the big problems. It reminds me of a lot of the problems I've had with modules because for some years, and you've probably heard me whip around about this inside the bar. But the trouble is that a lot of your criticisms is because modules as it currently is defined is trying to conflate two different things at the same time. So you have this component layer, which Microsoft, of course, did as a component object module a very, very, very long time ago. And it could be argued that that is the way to abstract apart things. One way of doing it, I'm not saying it's the best, but it certainly heads in the direction of making reusable components that are well defined, well separated. You know, there's a definite formal boundary between them. And then there's the other part, which is the build acceleration part, the part where you can speed up your build and do those things. It's always seemed to me that modules are trying to push those two together, and I've always wondered to myself that would it not be easier just to split those two parts apart? So you've got the build acceleration part on one hand, and you've got the really big enterprise software stuff on the other hand, and that would be beneficial to everyone.
Okay, so I think what was just said, which I'll boil down to the following. There's an architectural advantage to having modules, and there may be a performance advantage. I want to focus on the architectural advantage of modules and ignore the performance advantage for now. And once we get it right, then turn to look at the performance advantage without affecting the architecture at all. In other words, there's no backward push, there's no change. It's just, this is what you got, now make it fast. And I say that tongue in cheek because we already know how we would make it fast, and it wouldn't change with the kind of focus that I'm giving to the architecture. It wouldn't change at all. That makes sense. It doesn't affect it at all. So let's not think about performance right now. Let's think about what we want, and then let's think about making it fast. Is that okay?
Well, where I'm coming from is that modules at the minute is trying to preserve an awful lot of source code compatibility, and my big issue with that is I think that makes things so much harder, and if we just accepted that we need a new way of encapsulating things that is separate and new from the existing way of encapsulating.
Okay, so your statement is that it's okay to, in your opinion, fork the language and keep the old stuff the way it is, and then let the new kids do the new stuff, and never the twain shall meet. That's what you're suggesting.
Well, what I'm saying is the standard practice could be argued is Microsoft COM, and I'm not saying that we should standardize that because it's terrible, but what you could do is you could modernize and improve upon it, and then standardize that as being accepted as practice.
Okay, at this point, let me go on to the second part of the talk, which is pretty much going to disagree with you completely. Here's some questions that if you didn't ask them, this is the kind of questions I wanted, not those kind of questions, because that's the second part of the talk. I want to make sure that everybody understands these things. So take a look at this and tell me if you're a little bit more prepared than when you came in. I want to leave a little bit of time to talk about what we need in modules for real. This was just the background. If anybody has one of these that didn't sink in or they'd like me to repeat it, more than happy to do it. Still have 25 minutes. We're okay. Can't believe I have time in a talk. I think I'm going to make it through this one. It's also the shortest talk I've ever given at ACCU by far. Only 200 slides. Terrible. Not, it's just maybe even fewer. This looks like it's maybe even fewer than that. Maybe 150. Okay, so what do you think? Is this good? How about this one? Can somebody explain to me how do we extract component dependencies effectively using the rules that I suggested? In particular, the fourth property of components. What do we do? What tool do we use? We use grep for what? For pound includes. We get the include graph, and that becomes the envelope of physical dependencies for our components. So includes are really important. That's how we do it efficiently, 10,000 times faster than Clang. All right. Why would we put an include in a header? What would be the overriding reason to do that?
We have to.
We have to? In order for the header to compile. That's the correct answer. What's generally associated with the cost benefit associated with insulation? Why would I want to insulate a detail? What would that buy me? Okay, so it would allow me not to recompile. It would allow my client not to recompile should I decide to change my implementation. That's what it buys me. But it buys me more than that. It's not just improving compile time. If you have a three-tiered deployment strategy where I'm infrastructure, I've got middleware, and I've got end clients. And my end client realizes that whenever I create a hash table, I allocate 100 nodes and sew them together. And then my end client decides to create an array of 10 billion hash tables, each with one element. And it blows up memory. And they come to me and say, John, we need to fix this today. By the way, this happened. It wasn't 10 billion, it was about 5 million, but it didn't matter. I had to fix it that day, and the middle people were on vacation for a month. And even if they were there, they still wouldn't have released in any reasonable time. What did I do? My allocation strategy was insulated. I made a change to go from 100 to 32 and then made it adaptive. And then I took a .0 and I put it on the link line, and the problem was solved that day. And that's only because that detail was insulated. Otherwise, I would have a different job. So that's the benefit. What's the cost generally associated with insulation? 2 words.
Indirection.
2 words. The cost is runtime, which is 1 word, performance. Runtime performance is the cost of insulation in many cases. If you do partial insulation, sometimes it's negligible. So partial insulation is your friend if you want to get just the key parts. And I'll have you know that the technique used to insulate just the memory allocation for the hash table was partial insulation. And that was in 1997. Okay, let's go on to this. This is the second part of the talk. It's much shorter because this is talking about the good things about modules today. So this is a paper that I wrote in an evening. And rather than put bullets or whatever, I just highlighted the important points. And so here they are, and I'm just going to point them out. People feel that modules is a critically needed feature for a number of reasons. One of them, it seems to be very pervasive, is to reduce protracted build times. I'm not buying that. I don't think that that's a reason. It may work out to be so, but in fact, the way that that would be achieved has nothing to do with the design of modules and has everything to do with deployment. So it's not clear that that's an issue. It will result in build artifacts. There's no way that modules by themselves are going to do anything. What's going to happen is, as a result of build artifacts, also known as caches, we're going to pre-compile some headers. We know what that means. There are consequences associated with that, and if that's the only way to do business, modules will not survive. There has to be a way to build module code from module source the old-fashioned way. That doesn't mean there isn't an optimization that when you're turning the crank during development that you can't cheat. I think everybody knows when you say make dependencies and you get some dependencies, you use that for a while until it gets stale, then you rebuild that and then you do it again until it gets stale. People know this kind of thing. You do it because the worst thing that happens is you can't build your thing because it's stale and then you redo it. But you don't redo it every time because that's expensive and it's not necessary. The most important thing that I want to say is if we don't take into account the massive code bases that Google and A9 and Microsoft and Facebook and Bloomberg have, this will never work. It won't work. I'm not kidding. It won't work. And so it just won't work. So we need to do something. So the idea of this paper that I wrote, it's only 3 pages, was to say, please satisfy these requirements. If you satisfy these requirements, I don't care what the syntax is. I don't care. Whatever you want, just satisfy these requirements. So that's what I was supposed to talk about today, are the requirements, but I'm talking about them in terms of what we do as software engineers when we don't have modules. So what do we want? So it is a true story that I asked the question of someone at a previous conference after they talked about modules. So I work at Bloomberg. How would you advise that I use modules in my day-to-day life? And I believe it's almost verbatim, but we can go back to the video because it's there. It's 5 minutes at the end of the talk. And the answer was, well, are you able to change all of your source code and all of your client source code in lockstep? And I was at a loss for words. I said, I wish there were a stronger word, but no. The response was, well, you're over-constrained. Okay, thank you. So I'm just saying that it's not going to work. So Don Knuth said, asserted that premature optimization is the root of all evil, and I guess I'm claiming that we're on a road to premature optimization of modules without considering all the good benefits that they can have. That benefit will come. So let's get on to requirements. I came up with 4 requirements. They are additive, hierarchical, incremental, and interoperable. And what I mean by that, additive means, and I mean this literally, I don't have to change one line of my code that lives today in order to start using modules. Not one line. And that's a hard requirement. If I have to change one line, ain't using them. Sorry. But that's the requirement, because if I have to change one line, multiply that by how many things I have, and that's a lot of lines. So, okay. The next one, hierarchical. This might sound obvious, but things at a lower level aren't allowed to depend on things at a higher level. And you might say, well, how could that happen? And I offer global variables as an example. If you use extern int I in a lower level, and then main defines I, you basically have a dependency up. So that could happen. Modules today have implicit dependencies. Modules that are proposed, you don't even know where they are. That's another can of worms that has to be fixed. There is no specification as to when a module depends on another, how it depends there. It's kind of left in the ether. Not good. Okay. So the next one is incremental. Let's say I have one team at Bloomberg that wants to use modules. Does that mean that every team at Bloomberg has to use modules? The answer is no. The answer is yes, I'm not using modules. Full stop. No. So any team can start to use modules independently of any other team. Now, that's not independently of customers, but it's independently of other teams. So if I have a client that is willing to use modules, and I have a team that's willing to use modules, and I have another team that's not willing to use modules, the client can still consume the information from both, and it works. And by it works is interoperable. If I have something defined in a header file, exposed or ported through a header file, I have the same thing imported through a module. By the same thing, I mean I have my date class at the bottom, and I have something that uses a date class and traffics in it, and I have something else that uses the date class and traffics in it. And this is written in terms of components, and this is written in terms of modules. And somebody consumes both, and both of them spew out a date class. It's the same date class. Does that make sense? It's a lot like a C procedural interface. And that's even documented in the 1996 book. You can see that you can have a procedural interface where all you need to do is pound include the header, and the C procedural interface becomes a C++ procedural interface where the opaque name is actually the type that you had underneath. That's exactly the property we need for modules. Nothing else will do. Okay. So, some things that modules can deliver is logical and physical encapsulation. And the example there is I have a box that I expose. It's implemented in terms of points, but the interface is purely integers. So I say, set box, lower left, upper right coordinates, so 4 integers, but internally I have 2 points, lower left and upper right. I do not want my client to start using point because it's temporary. I'm going to replace it with something else sooner or later. I don't want the client to start using that. Modules can help here. What it'll do is, in current component speak, if I have a private thing used, I still have to pound include in the header, still have to include the points header. And once I do that, the client is at free rein to use a point as if it's a public thing. Now, modules can forbid that, which means that the rule about include only what you use will be enforced by modules. So if you don't include the point directly, you won't be able to use it. That's extremely valuable. It's one of the biggest problems we have at Bloomberg is transitive includes. And when we go to change something, we break clients. It's not our fault. We never said that that imp detail was for you to use, but you assumed it and used it anyway. So this fixes that. That's awesome. The second one is modules should be atomic with respect to compilation. And the best example of that is coming up with contracts. If I have built something and I want it to be in a very aggressive mode with respect to contract checking, so I say I want to be in debug mode or even audit mode, which means that everything I can check is checked. And I build my module in such a way that that's on. Any client consuming that module should have the functions that emanate from that module, the interfaces, the contract should be audited and not determined by how the client is built. Right now, if I have a template or an inline function, it's the client's build that determines the level of assertions that get used, even though it's from another translation unit. It's from another component, okay? That is a huge problem. And it means that we really don't have the physical modularity, along with not being able to say that something's private when we're giving it out. We also can't say what our build modes are, and that's unfortunate. So the way that gets dealt with, as I've learned recently, is it doesn't have to be part of an artifact. It can be done with metadata, where you say, okay, that's the way this module is. Whatever that is, this module is like that at the source level. And when it is built, whoever builds it will build it like that. As opposed to saying, I built it, here is the thing, and it's already built completely, and it's like a .o, but it's not. It's an ABI-compatible black box. Doesn't have to be that way, but that is one way to do it. And that is the way that the compile time optimizations will most likely occur. But as far as the semantics go, you need to be able to say that a module has this level of assertions on. That's what this configuration looks like. You depend on that configuration of the module. Okay. So I guess this one is, we need to be able to not change anything and add something, and that should work perfectly well. And we should be able to provide a view. Now, this is more than what we have today. Today, if I were talking in the second talk, I'd be talking about, suppose I want to provide a view on a subsystem. And I have different clients, and some are really smart clients, and they're like our first users. And the view that I give them will be the latest and greatest, and they'll be dangerous, and it's okay because they'll be using them. But then there are other much more routine clients that need stable interfaces. So I could have two modules, and the modules would provide a different level of capability on the existing software. For example, some classes would not be provided under that view. And in fact, some methods of some classes would not be provided under that view. And then if a client made use of that and another client made use of another one, and you took the union of the capabilities, that's what a client using both would inherit, the union of the capabilities. So if I had a stack that had push for this client and pop for this client, and they were exported to another client, that stack would have both push and pop, because the union of the capabilities would be merged. And that's something that that modules could eventually do someday, and is something that's needed in practice because the alternative is wrapping. And if you wrap something in a single component, it can be sprawling, it's not scalable. If you try to wrap something in many components, it's not implementable because it causes long-distance friendship typically. And so there is a solution that's really gross that takes an entire package and wraps another one, but you still have the lack of interoperability because the wrapper package is not truly the underlying type, and they're not interchangeable, they're not substitutable. So what we would get from this is effectively a procedural interface, but with objects. So really like a procedural interface on steroids. And if you read Lakos 96 and you look at procedural interfaces, modules are the object-oriented version of procedural interfaces in that sense. Procedural interfaces are insulating, by the way, whereas modules are not, but then modules don't incur the overhead that procedural interfaces do. Okay. Whoops. Did I do that really? Okay. And the fourth one, I just said that. Okay, this slide. I went on ahead. So there's a reference here. You can actually go look and see where I'm talking about this particular property. But this is a higher level property. This is an architectural property where we're trying to look at a software system from a facade, where the module acts as a facade as opposed to a component. So the module is at the package level as opposed to being at the component level. It's a different level of abstraction. And it could have a white list, could have a black list, depending on whether you say, I don't want to expose these methods or I want to expose only these methods. That's all to be determined. That's just capabilities. Now, the real world scenario that must happen, if I have an existing system like this where I have, let's say I have a library and I have a subsystem, and now I decide to create a modular interface for this header file built library. I could do that. Say I do that. And then somebody else comes along and consumes that module-based library. They're working exclusively in modules. And now somebody comes along and they want to consume my module-based library and this old header file-based library. That should be possible. And again, if the same type is exposed with different capabilities, the top-level client will get the union of those capabilities, not the intersection, not one, not the other. And that's the only way it can work. And so it's simply saying the more you include, the more capabilities you get, but there's no ODR violation. Now, the interesting thing is there's no guarantee that someone will ever change to have a module interface. It may be that there are C libraries that will never have a module interface. And that's okay, because you can still use headers. Or you can provide a module interface without changing the existing code. So somebody else, a third party, could provide a module interface for an existing library. But if you tell me that in order to provide a module interface, I have to change the existing library, it's over. It's not happening. Full stop. And that's just the way it is. So, when I say the Google approach, I don't know enough about it, but it's what I saw a year ago, and I understand that progress is being made and things are evolving. So please take this with a grain of salt. This paper was written, and then it was read, and then things happened. So this is a year old, almost. Anyway, I mentioned that having a cache, necessarily having a cache, could be very problematic. Once all of these things are met, and by the way, the fine-grained views are a want-to-have, not a must-have. The others are must-haves, absolutely deal-breaking requirements. And the views are it would be nice, and I can wait. Just so you know, they're not all the same. First four, absolutely. Last one, it would be nice. But once we have the first, then, and only then, should we talk about optimizing, and maybe we'll build it from source today. Maybe later we'll have this optimized build where we can actually do things faster. But keep in mind, if we have artifacts, instead of being able to build every translation unit at once in parallel, we will create a dependency graph so that lower level translation units, in order to be translated, you'll have to have translated the lower level ones first. So we'll create a build order dependency where none previously existed. Does that make sense? So right now, if we had an infinite number of computers, I could compile all translation units in the universe in parallel. With this newfangled deployment strategy, that is no longer true. So build times will have a negative impact in that respect, but a positive one in the sense that the lower levels are typically stable and don't need to be rebuilt so often. And so in practice, we do expect to see an improvement. But that's down the road. Okay, so there are many competing ideas. The purpose of that paper was to give you something to think about. Any questions, and in particular, what are the engineering requirements for modules? Do you know? Does anybody have an idea of what they want to see in a module now? Because that's the purpose of this talk, is to have you demand what you want in a module. Yes?
Yeah, well, I'm in game dev, and we want modules to be we want the speed though. Speed.
Compilation speed.
We want what you also said. We want that insulation and nice encapsulation.
Okay, remember there's no insulation, there is encapsulation. There's physical encapsulation, there's no insulation. There never was, I didn't take it away. There never was any insulation.
Why isn't there insulation in modules?
Because the way it was proposed, the question is why isn't there insulation? What we're doing is we're taking the interface and we're putting it at an ABI level. But the thing that's a problem is if you change the header file, that's source code. If you change the interface, even though it's not source code, it's still the interface. And if you change the interface, there is a build time dependency on that interface, even though it's not a source level dependency. And that's why when that build interface changes, you have to recompile. Just like if it were a header. There's no difference. Think about what's happening. A precompiled header is great until it changes. Then you have to recompile the precompiled header. Right? Now, I'm not talking about a space change. I'm not saying, oh, the file stamp changed or whatever. The idea is if you substantively change the interface, then you have to recompile. That's what insulation is about. Whereas if you insulate a detail, you can change the interface of the detail, and the client of the thing that's in the detail doesn't have to recompile. Anyway, I hope you want the first four things that I talked about because they're important. And the last thing that I wanted to say, which is the conclusion, is remember these things. A component is the fundamental unit of logical and physical software design, and a module would replace it. No cyclic dependencies, no long-distance friendships, and a module would enforce that without exception. We would collocate constructs only with good reason That's a design decision that modules support but don't require. And fourth, we would include only for good reason is a has a inline enum and typedef to template, and that doesn't change with modules. And that's the end.